Good afternoon. We are going to directly share the screen and go and add some extra information to the chapter on the decay heat generation in nuclear reactors before we go to the next step. And we suggested in the last chapter, that's where we stopped, that decay heat generation can amount immediately after shutdown to about 6% of the fission reaction power generation. So we did some simple calculation here, and that graph shows it, that immediately after shutdown at 0.1 second, 0.7 second doesn't really count, but you could see here, this is a log scale that's 2, 3, 4, 5, 6, 7, 8% of the power that is generated from fission is still being generated from the decay heat. That's designated as decay power. Percent power means that this is the decay heat power generated relative to the thermal power of the reactor. If you do not extract that heat, you'll find that the energy generated keeps increasing, integrated, and at some point within, say, a day, it can cause significant damage to the reactor. The decay heat itself decreases quite rapidly on that scale, on a logarithmic scale. So initially it's 8%, but say after maybe 1 hour, it's already 1%. After 1 day, it is 0.5%. So it decreases rapidly. So the crucial time is the time 4 hours maybe where we have to provide cooling for the reactor after we shut it down. If we fail in doing so, we melt the core. If you melt the core, you release the radioactivity to the environment, especially that we are using solid fuels today. We use the solid fuel, and we try to contain the fission products, the radioactivity in the fuel itself. In an evolutionary way, we would like eventually to move from solid fuels to liquid fuels. In that case, you would extract the fission products continuously. And in that case, we do not have the occurrence of the 3 Mile Islands, Chernobyl, as well as Fukushima. All of them have been related to the decay heat generated from the fission products in the solid fuel. Here we integrate that decay heat, and we define what's called the adiabatic cooling extent in the pressurized water reactor or the boiling water reactor. And it amounts to about 4 hours. If you don't cool the system, you can get very serious damage. I showed you a procedure here that calculates the logarithm of the power generated within a reactor that operated for 1 week, 1 month, 1 year, and 10 years. This is a procedure here that calculates this amount if you ever need to use it, say, in an operational or a design type of an environment. The total heat generated is an integral of that power, integrate power. You get, over time, you get energy. You could see that a reactor operating for 10 years would have much more decay heat generation because of the accumulation of the fission products. Usually we exchange the fuel of the reactor. Reactors are refueled once every year. So the 10 year is just for information. This becomes really the highest level that we can generate within a year. This is a graph that would be relevant in that case. Now, what are the safety implications? If you look at how much energy is generated, if you do not cool the reactor after you shut it down, you'll find that within 1 day, you have generated a significant amount of energy. It's 18 megawatt thermal day. Remember, megawatt is 1,000,000, watt thermal is joule per second, multiplied in today's, these are units of energy. Within a month, you would have accumulated 191 megawatt thermal day of energy. As that energy accumulated, we get consequences in the reactor. For light water reactor here, you'll find that within 10 to the 4th second, you start generating enough steam to be a threat to the piping system. So you have to release that heat from safety valves shown here on top of the pressurizer unit. That's for a pressurized water reactor. So you start getting, and here at that point, after shutdown in seconds, you get superheated steam. The core now is not being covered with the water to be cooled anymore. So at that point, that triangle here means that you have now a threat of damage to the reactor core. Not only that, but because you have such high temperature steam, the steam can interact with the metal, the cladding, oxidize it, basically burn it if you want to call it this way. The cladding becomes brittle, it turns into a powder, and the fission products that are contained within the cladding are released to the environment. So this arrow here, as you could see here, is fission product is escaping. The triangle means danger of plant damage. And this here symbol means relief safety valve lifts. Now notice that this is at an operational temperature of about 350 degrees Celsius. This is the operational temperature of the pressurized water reactor and the boiling water reactor that we have today. If you operate a system with a higher temperature exit there just for municipal heat, like on campus, we have a plant that uses coal and natural gas to heat the campus. You can have a nuclear reactor. In that case, it would be a pool reactor. You will not get to the level of plant damage until maybe a whole month. You can even bring, say, water in a truck and pour it into the core. This type of a system is designated as a secure system. So there's a graph here, number 4. Only after maybe 30 days, you start, if you do not add coolant to the core, you'll get a core damage. 3 here is this graph here is the existing PWR. We can do better by using graphite as a coolant. That's 2 HTGR. You'll find that you operate at a much higher temperature, 1000 degrees here. You have also a graphite core, and graphite has a very high thermal inertia. It can absorb lots of heat. You find that the temperature increases and reaches a maximum and then comes down. The mean temperature, in fact, increases and comes down, and you get the threat of damage to the plant damage only within maybe a whole day or more. You can do even better with a different design of a high temperature gas cooled reactor shown here in the 2 graphs on the top. You could see there, if you use in that case an annular core, so you'll find that heat would be escaping from the center of the shell, in that case the annulus, and from the outer surface. So you can reach very high temperatures without ever reaching that point of plant damage. The top here shows us how the different barriers against the release of radioactivity can be breached. At that point here, that's a adiabatic cooling accent, theoretical accent for the PWR. You'll find that you have to breach the rod plenum, the rod that contains the fuel, from the coolant area, from the containment structure, and then from the containment wall at different stages of the extent if we do not cool the decay heat generation. If that was the case that we have to live with for pressurized water reactors, oh, well, fine, that's maybe we have to live with it and implement the engineered safety features to benefit from nuclear technology. But that is not the case. You could see here that by switching to gas-cooled reactors or high-temperature gas-cooled reactors using graphite in 2 different forms, either like a whole core or a pebble bed, or here as an annular geometry, you can reach really 3,500 degrees without any danger of plant damage. So in that case, it suggests that we need to replace the existing nuclear power plants by a new generation. Our nuclear power plants in the United States, Europe, and Japan have reached the level of 40 years of operation. Even in Japan, they're trying to extend that life after a safety review to 60 years of operation. This is beyond any kind of technological system in terms of adding renovation and innovation and improvement to the existing designs. After Fukushima, the Germans realized that their reactors at 40 years of operation are in some form of risk, and they are shutting down their old nuclear power plants. That hasn't been the case in France. France depends on 70% of their power, electrical power, from nuclear power stations. Just here, getting into the winter, they have several of their plants shut down for maintenance. So even the French fleet of nuclear power plants is getting too old. Japan has decided that they cannot really depend in their economy on the use of natural gas. So they're extending the life of their reactors after a safety kind of review to the 60-year life. The longer the life of operation of those plants without replacement by new fleets of plants, the higher the risk that society in the whole world, in fact, entails in terms of getting reactor accidents. This shows us a difference between the different reactor fuels in terms of operational temperatures. You notice here that the boiling water reactor and the pressurized water reactor operate at operational temperatures in the range of 300 to 320 degrees Celsius. That is a very low temperature. If you go to the liquid metal fast breeder, you get to 750, as well as the advanced gas-cooled reactor that was used in the UK, and the magnesium oxide cladding Magnox magnesium oxide, that's a type of reactor. You can reach their temperatures in the range of, they have been reached, in fact, 750 degrees. So that entails, of course, a higher efficiency of operation, as well as the ability to reach higher temperatures so that we can generate hydrogen from water. So you turn the nuclear energy into another form of storing energy, hydrogen, by using high temperature electrolysis. The electricity electrolyzes the water into hydrogen and oxygen, or you can go to the high temperature gas cooled reactor using helium as a coolant, not listed here, but that can also reach the 900 to 1000 degrees Celsius, meaning higher efficiencies, and the possibility of using high temperature electrolysis, as well as thermochemical processes for producing hydrogen fuel. The cladding here, of course, is a barrier for the release of radioactivity. You'll find that the temperature distribution in the fuel, this is a radius of about 5 millimeters here, as you could see. So the radius of the fuel is maybe no more than 1 centimeter. You have a cladding here, clad made out of zircaloy. Zirconium resists corrosion. That's why it's used as a cladding, as well that it has low absorption for the neutrons. The pellets, the uranium dioxide pellets in the PWR and the BWR are inserted into that cladding. There is a gap between the fuel and the cladding, and it is filled with helium. Helium, in that case, acts as a bonding agent for the heat transfer from the fuel itself, the uranium dioxide, into the clad, as you could see here. The temperature drops, and then eventually you get your coolant to circulate on the outside to extract the heat. Notice that the temperature at the coolant level is quite low. We said that it's 350 degrees in water. And it depends also on the start of life or the end of life of the reactor fuel. At the end of life of the reactor fuel, a void forms in the center, and the heat, the distribution of the temperature is slightly higher than at the start of life. So you have a void here in the center. But look here, the temperature at the center of the fuel can be reaching about 4,500 or even 5,000 degrees Fahrenheit. And but when you get to the coolant, it's only 350 degrees. This is Celsius temperature. It's 3 times the boiling temperature of water, no more than that. So suppose that you are doing a design calculation, or you use our little computer code here that I have given you. At the time of the Fukushima accident, many people used it just to estimate the heat. It's a very simple code that we can use. However, the operators at nuclear power plants do not have time to use a code if there is a need to know how much cooling they need to the reactor. So they depend in that case on ready-made calculations in what's called the reactor analysis handbook or system analysis handbook. So basically those calculations have been put into graphs, and this is one of the graphs that they use. They show the decay power in megawatt thermal. Here they should add thermal of decay heat per megawatt thermal initial. That is our P naught in our equation, P sub 0, which is the operational pressure, the operational power of the reactor as a function of the time after SCAM. Notice, be careful with the hours. Some textbooks use seconds as on the time scale. We use days on our time scale. This graph uses hours on the time scale. This is a log-log scale, so you could see the range goes in decades, factors of 10, 1, 10, 100, 1,000, 10,000. And here the ratio of the decay heat generation to the initial power also goes in decades. Why do we use a log-log scale? Because the range of variation is quite large. Here we go to 10,000 hours, and this is 0.1 hour, or like you can say it's 6 minutes. The correspondence between those graphs and what we have generated in the computer code and our derivation are similar. I should give you a problem where you compare the two, depending on how long the reactor has operated. So this is a reactor that operated for 10 days at fixed power here. That is 100 days at fixed power, 1,000, 2,000, 5,000. And then they keep increasing it and they give us an infinity. There is no infinity there, but maybe a reactor that operated for 5 years or 10 years. They take into account the production of actinides, that 1 atom of uranium-239 per uranium-235 fission has occurred. They do not consider neutron capture in the fission products, and they do not consider fast fissions in uranium-238. And these are generated by very sophisticated codes like the RELAB 5 code. That's a code that simulates the behavior of PWR. It has been updated also to simulate the behavior of boiling water reactors. So immediately after shutdown, that reactor handbook here tells us that, well, if you go to 1 second, the relative power of decay heat to the fission power is maybe 10 to the minus 2. So it is really 100 only. So that's within 1 hour after shutdown. Immediately after shutdown, you'll find that it is now not the decay power would be maybe 2 to 6% of the thermal power. So if you take the thermal power as 3,000 megawatt thermal and you take say 10% of it, that's still a significant 300 megawatt thermal that you have to cool the reactor at in terms of providing auxiliary sources of water. In the BWR, we have the condensate storage tank and we have the pressure suppression pool. In the pressurized water reactor, we have the refueling water storage tank and the accumulator tanks that contains water under nitrogen pressure to provide sources of cooling. Again, this is what an operator would use when he's operating his nuclear power plant. In the system analysis handbook, you'll find also some other interesting information which we derived by integrating the power. Then that describes us the total energy generated. So you'll see here that the energy generated also matches what we have done. And depending on the energy generated, you would have to provide cooling or else your reactor would get damage from the decay heat. And it happened in the 3 major accidents that we're going to analyze later in general. So how do we do the calculations? We take an example of a reactor that operated 100 power at a steady state of 1,000 megawatt thermal, shut down for 80 hours, and then operated again for 10 hours at a steady state power of 500 megawatt thermal before being shut down. And in that case, we wish to estimate the decay heat power 20 hours after shutdown. You notice here that we have two periods of operation, one for 100 hours at 1,000 megawatt thermal, shut down for 80 hours, and then operated for another 100 hours at half the power level of 1,000 megawatt thermal. It turns out that the decay heat after shutdown, luckily, or because it's simple, is the linear addition of the decay heat from the two periods of operation. So what do we do here to estimate the total decay heat? We take the first period of operation at 1,000 megawatt thermal, substitute for the equation that we derived for the decay heat power, and we can determine the power that is generated after from the 100 hour of first operation. We calculate the power generated from decay heat at the lower level, that was 1,000, this is half the power 500 megawatt thermal, and then we add the two linearly after the period of time that the reactor has been shut down. In that case, the P1 gives us 0.45 megawatts thermal of power, and the second period of operation is 1.5, so the total adds up to 1.95 megawatt thermal. And I gave you a problem similar to that, simply to get an idea about how really operators have to determine what is the decay heat generation in their system. The equation that we derived is a very simple equation. The reactor systems handbook also is a very simple equations, but many other people derive alternative equations that people have used in different ways in the design and the operation of nuclear reactor. Two people, for instance, Way and Wigner, derived an equation for the beta and gamma decay for the fission product. I combined them together. In our case, we took them together, and T here is the time after irradiation. You'll find that if you use that equation, you get double the decay power from what we have derived as our equation. A more accurate representation is given by an empirical relation. P would be the decay heat power, P sub 0 is the fission power. A much more difficult equation. It takes into account in the same way as we derived our equation, the time of operation of the reactor, T sub 0, and then calculates it at T, which is the time after shutdown. Why is it that relationship more exact than ours? Because they take into account the contribution from the uranium-239 and neptunium-239 that are basically generated as we operate the reactor from radiative capture, meaning that a neutron is absorbed in uranium-238 here. And usually we have neptunium-237 generated in nuclear power plants. This one absorbed 2 neutrons and became neptunium-239. Neptunium-237 is an odd number isotope, so it fissions as we operate the power plant. But if you get the 238, it absorbs a neutron and becomes neptunium-239. So they take this into account in that equation 18. If you want to take them into account, you have to use that equation. If you want to take into account the heat generated from uranium-235 fission, you can use another equation. You subtract from it the generation of heat from neptunium-239 and from uranium-239. These are the approximate relations in that case. Okay, here we make a simple discussion here that nuclear reactors are very different from any kind of classical boiler or a steam generation system. The decay generation decreases rapidly after shutdown, and it becomes a small fraction of the operational fission power level. However, in terms of safety, the safety design of nuclear power plants must include provisions in terms of pumping facilities and decay heat exchange equipment that accommodates that heat generation immediately after shutdown. If you do not provide enough cooling within 2 hours, you can melt the core of a PWR or of a BWR, and that's what happened in the 3 major accidents, the 3 Mile Island, Chernobyl, as well as Fukushima in general. So it is crucial to include provisions in terms of pumping facilities and decay heat exchange equipment that should accommodate the decay heat generation. And I here emphasize immediately after shutdown. You don't wait. Within a fraction, between seconds, you start cooling, which would amount to about, in our estimate, 6% of the operational power level at 1 second after shutdown as we calculated it. So if you have a 3,000 megawatt thermal reactor, 6% means that you have to provide 180 megawatt thermal of cooling immediately after shutdown. People who didn't know that, this is the typical of the Chernobyl accident. The operators made a human error in that they didn't basically account for that decay heat generation. Spent fuel elements also that are stored in fuel pools on reactor sites. You know that after you use the fuel, you store it in pools at the reactor sites for several years to get the radioactivity to decay down and cool down before you take it out for reprocessing or for disposal. So you find that it is not a good idea to keep that fuel in the reactor pool, because at Fukushima, the loss of power from both the plant itself and from the outside grid prevented the cooling for those fuel pools, and there is indications that there have been damage to the fuel in those pools. So that fuel that is stored in the fuel pools should be recycled or processed to get rid of that decay heat generation. So decay heat I have here, by the way, in the assignments, another relationship for the decay heat power, and that's an American Nuclear Society Standard Institute. That's what the American Nuclear Society suggests we use. It gives us an expression for the decay heat power relative to the fission power in this simple form with a constant here in the front. And that constant varies for basically for the different times after shutdown. A is for the period from 0 to 10 seconds. A takes a value 0.18 for 10 to 150 seconds, and A takes a value 0.13 for the time after shutdown, 150 to 4 million seconds. All right, so in that case, you can derive an equation for the total energy release between time T1 and T2. All you do is integrate each one of those variables, and then if you have a 3,000 megawatt thermal, you can calculate the decay heat. The reactor physics, the handbook, not the reactor physics, but the system analysis handbook depends on using the code that was generated at the Idaho National Engineering Lab. Mr. Vic Ransom is a person with many other people. He became, after he left the Idaho National Engineering Lab, he became the head of the Department or School of Nuclear Engineering at Purdue University, our neighbors in Indiana, and I had the pleasure of working on parts of this code at the Idaho National Engineering Lab and applied it to a space reactor. It was called the SP100 for space reactor, 100 kilowatt, generating enough electricity to man a radar that can detect fortifications for the military underground. So if the Iraqis had tanks underground, then that reactor in space would detect them in that case. All right, so here we can start on another chapter that has to do with what happens after a melting core. And if you melt a core, this is what happened in the 3 Mile Island accident. Those lines, vertical lines here are the fuel rods. And because there was no cooling, enough cooling for the decay heat, the rods in the center, because the power level in a reactor peaks radially at the center towards the outer radius, and also axially at the center. Here you find that the power increases near the center and then comes down. The 3 Mile Island was a PWR, so most of the cooling happened in the center rods. All the other rods here They're still there, but now the core was did not have enough cooling, so the cladding oxidized, it became powdery, it collapsed, the fuel fell to the core, and you find that we have now a debris bed here. And the different parts of the core now are cladding that's oxidized, these dashed lines here. Cladding oxidized, ruptured, embrittled, and fragmented, those crisscrossed ones, severe fuel damage, and also a formation of an alloy or eutectic. Eutectic is an alloy between two different elements. In that case, zirconium and uranium dioxide formed an alloy. This is the white part here. Big, really damage here. The uranium dioxide and zirconium formed also eutectic, an alloy, and zirconium blockages. And this part here is the, I think that's the intact core here. They made a fuel, there is an error there. But evidently, now you have in the center of the core a debris bed after the 3 Mile Island accident. And that bed here had to be continue being cooled. If you wouldn't continue getting it cooled, it would melt again. And the melting can go through the lower support plenum here and interact with the lower part of the reactor. In the 3 Mile Island, that core did not melt through the bottom part of the core. But in Chernobyl, as well as in Fukushima, there has been melting through the bottom part of the core. It was these were two more serious accidents. So the question is, how do we continue cooling that core? And that core operates, interestingly enough, almost like a pressure cooker. If you have cooked rice and you observe the rice basically cooking, you'll find that some chimneys form in the rice bed. So a chimney here where steam is being released, steam being released, steam being released. And if you pour liquid from the top, the liquid falls to the bottom and then leaks out of those chimneys in the rice cooker, in fact, and the steam rises from the center. So that's a debris cooling chimneys cooling the rice cooker model. The late Professor Jones, myself, and a PhD candidate in that case used that model to study the process of debris cooling without having to generate an accident and then look at the debris cooling. We have a PhD student who is proposing another model. He hasn't even seen that model, but he's proceeding with a different approach using actually experimental beds in general. So we have different forms of cooling the bed. If you pour water from the top, you'll find that the water leaks to the center, to the debris bed bottom. Vapor is formed and goes up from the surface if you do not consider that more sophisticated model that uses basically the rice cooker and the generation of chimneys. And the rice cooking is a very, very interesting analog, in fact, of what happens if you try to cool those debris beds. So there is a situation also where the debris bed from the accident would be multi-layered. So you'll find that some part of the core, when you pour water on it, you get at the bottom boiling. At the very, very bottom, the liquid accumulates. It starts extracting heat from, what is that heat from? That's from the decay products. You can call it after heat, but that happens over now months and years maybe. You get vapor generated, and then as you are pouring water from the top, there is water on the top, the vapor bubbles and escapes as a vapor from the top. So this is another model of a multi-layered once through debris bed cooling. Experimental observations wise that we would like to bring to the attention of people, the debris cooling efficiency is dependent on the particle size. So it depends on the process of damage that happened to the core. And for a 1 meter deep bed with particles 4 millimeter in diameter, half a centimeter almost, you find that you are generating 750 kilowatts per cubic meter. So it's a significant amount of heat generation. If the size of the particles is very small, 0.1 millimeter, you'll find that the heat dissipation rate falls rapidly to the 20 kilowatt per meter cube level. A typical debris bed can have a decay heat power generation rate from the fission products of about 1 megawatt per cubic meter about 3 hours after the accident. So if you don't cool the debris bed and you have to cool it, you end up melting the core. So what will happen in that molten core in Fukushima, that molten core went through the pressure vessel down to the what's supposed to be a dry bed concrete. However, it had water, so there is a suggestion that there has been a steam explosion, and that's we'll give that steam explosion concept a whole chapter in our analysis. The French, though, are designing their PWR, or they call it the evolutionary PWR. There are units built in France and units built in Finland. Some people like to call it not the evolutionary PWR, but the European PWR. The company working on it is Areva from France. So you could see here that PWR, assuming that the core is going to melt down through the lower part of the pressure vessel. So they allow a provision where the molten core would be sent through a conduit here to an open pool where the core would spread out, and instead of using water to cool it, it will cool itself through radiation to the environment. And in fact, they're really implementing this as a safety feature in general. So in that case, they don't have to continue cooling the core if it melts through. The real difficulty is the size of the particles that varies as the accident progresses. If the accident is a short time period accident, the debris bed would have large particles. If the accident lasts for a long time, you'll find that the size would be smaller. The worst case scenario must be envisioned by providing a method of spreading the bed into a well-cooled pool in the case of an accident. And this is the philosophy of the European PWR, APWR, or the evolutionary PWR. So as I suggested, this provision is used in the newer evolutionary PWR by the French company Areva, where the corium material, corium here stands for the molten core, and that would be molten fuel, molten cladding, molten spacers, molten even control rods, and they spread it in a well-defined shallow pool that would cool itself passively through radiative cooling to the atmosphere. So all this problem of having to cool the core with water cooling is simply dissipated. Another issue here that is of concern, maybe when you spread the core like this, you increase the surface area of the molten material. So in that case, it cannot become critical and start a chain reaction outside the reactor core. And at that point, I'll give you an assignment on that topic here as an exercise, very simple exercise. Compare the levels of heat generation at diameter size of 4 millimeter and 0.1 millimeter and see how different they are. And I wish you all a nice weekend. We'll stop sharing at that stage. And thank you, Alvaro. I hope we got the audio detected. We didn't get it the last time.